Hello everybody, and welcome to exercise B, or exercise 10b. So we're going to continue what we did in part A. Part A asked us to build a Taylor series for ln of x, and now we're going to use that Taylor series to do an approximation. Okay, and in particular, they'd like us to estimate the value of ln of 1.1, and then to figure out what the maximum error in that estimate is. Okay, now notice how they're asking us to do that. They'd like us to use P2 of x, which is the second Taylor polynomial. Okay, so let's first remind ourselves of what that means. Okay, so P2 of x just means we're going to go to the series that we calculated here, and we're going to take enough terms until we get to the number 2. Okay, so that 2 that you see there is referring to the power of x. So we need to take these first two terms because of the fact that that's what leads us to that second power. So P2 of x is just the thing that I've underlined in red, those first two terms. All right, so the first part of B then is just going to be to take 1.1 and plug it into that P2. So we'll write down the first two terms in our series. Okay, and then that's a job for, you might even be able to do that in your head. That calculation is not terribly difficult to do. You could also use a calculator, that's no problem. If you do that, what you're going to wind up with is 0.095. And what we're saying is that that's an estimate of ln of 1.1. Okay, how good is that estimate? All right, well, that kind of hits at the second part of the question here. They'd like us to use the Taylor error approximation formula to find the maximum possible error in that estimate. Okay, let's review that process. That was a little bit involved. Okay, so to use the error formula, we're going to start by noting the value of n, which is 2 in this case. And you may remember, if you look back at that Taylor error formula, there was a number called m in it. And that number m related to the derivative that's 1 bigger than the value of n. So the upshot of it is we need to look at the third derivative of our function. Okay, we're interested in the absolute value of that. We can look back up here at our work and see that the formula for f triple prime is 2x to the negative 3. I'm going to rewrite that as 2 over x cubed. And the idea of the value of m is what we're interested in is what's the biggest possible value that 2 over x cubed could have. Okay, so in the language of section 8.5, we're looking for the max value m, and it was on the interval between a and c. And I'm going to remind you what those two numbers were. So c is just the number that we're plugging in. That's where we're doing the approximation. And a was given to us in the problem. A was equal to 1. You can look back at the top of the page and check on that. So we're asking, what's the biggest that 2 over x cubed could be if we look at x values between a and c, 1 and 1.1. All right, so ask yourself, if you look at this fraction, 2 over x cubed, where would that fraction be the biggest? If you just think about numbers between 1 and 1.1, well, the smaller the number you plug in, the bigger the fraction, and so that left-hand endpoint's going to give us the biggest value. Okay, so in a nutshell, this is going to be largest if we plug 1 in, and that 2 over 1 cubed, that's the value of m that we're going to use in the error formula. Okay, and so now we are ready to actually calculate the error. Okay, our notation for it was E2 of 1.1. And for this, you might need to look back at section 8.5 and actually find the Taylor error approximation formula. I'm just going to write down what it looks like. So it had the form m c minus a to the n plus 1, and n is 2, so we're going to get a 3 there, over 3 factorial. Now it's a matter of just plugging in the pieces. Okay, so m was 2, c and a are 1.1 and 1. Okay, and if you do that calculation there, Okay, I'll let you confirm that. You're going to get a number that's less than or equal to 0.00034. Okay, and that number is our maximum error. Okay, so to sum it all up, there were two parts to our answer for part B. There was this number, the 0.095, that was our estimate of ln of 1.1, and this number down here is telling us what's the maximum error in that estimate. It can be off by no more than 0.00034, okay, which is pretty good accuracy.